Detect loop in linked list. This question came up during my on-site at Amazon. What looked like a simple linked list problem turned out to be a test of whether I understood Floyd's cycle detection algorithm, something a lot of candidates overlook. And over 40% of candidates freeze on this logic. Today, we'll make sure you never get tripped up by a sneaky loop again. Let's crush this blind 75 must-know with a foolproof strategy. First, let's break down the problem. Given the head of a singly linked list, we need to determine if there's a cycle, meaning, does any node link back to a previous node instead of ending with null? As you see in the image, node 5 points back to node 2, forming a loop. If there's a cycle, we return true. If not, we return false. It's that simple. Let's assess our options. One brute force way is to remember every node we've seen using a hash set. But that needs extra space, ON. Is there a slicker way? Yes. The classic tortoise and hare method uses 2 pointers. One moves 1 step at a time, slow, the other moves 2 steps at a time, fast. If there's a cycle, fast will eventually catch slow. If not, fast will hit null. This technique gives us ON time and O1 space, super efficient. Now, let's structure our approach. Start both slow and fast pointers at the head. Move slow by 1 node, fast by 2 nodes each loop. If at any point slow equals fast, we found a cycle, return true. If fast hits null, the end, there's no cycle, return false. In the worst case, the time complexity of this algorithm is ON. Here, n is the number of nodes in the linked list. We visit each node once, and each check in the hash set is very fast, in constant time. Now, let's look at the idea behind this solution. We want to detect if a linked list has a cycle. A cycle happens when a node points back to an earlier node, forming a loop. To detect this, we keep track of all the nodes we've already seen using a hash set. If we ever see the same node again, we know there is a cycle. First, we bring in a special toolbox called hashset. Think of it like a magic notebook where we write down every node we've seen. It helps us check very quickly if a node has been seen before. Next, we define a function called hasCycle. It starts at the head of the linked list and will return true or false depending on whether there is a cycle. We create our magic notebook, the hash set called visited. This will remember all the nodes we have looked at. We also create a pointer called current, starting at the head of the list. Imagine it like a little finger moving along each node. Now we start a loop that continues as long as there is a node to look at. When current reaches the end, the loop stops. Inside the loop, we check if our notebook already contains this node. If it does, it means we've been here before. Bingo! There is a cycle. If we detect a cycle, we immediately return true. It's like raising a flag saying, yes, a loop exists. If the node is new, we add it to our notebook. That way, next time we see it, we know we've already been here. Then we move the pointer to the next node. Step by step, we walk along the list. If we reach the end of the list without seeing any repeated node, we return false. That means the list ends normally, with no cycle. So, to sum up, this algorithm sets up a hash set to track visited nodes. It walks through the linked list step by step and detects a cycle if any node is visited twice. It's simple, clear, and efficient. The hash set lets us check for repeats instantly. We only visit each node once. In the worst case, the time complexity is ON, with n being the number of nodes. Let's check if our hasCycle function works. We want to see if a linked list contains a cycle, where a node points back to a previous node instead of none. We test it with 3, 2, 0, -4, and pos equals 1, meaning -4 points back to node 2, forming a cycle. The function uses a set to track visited nodes. As we move through the list, we add each node to the set. When we reach a node already in the set, we detect a cycle and return true. The output is true, confirming the function works. This implementation correctly detects cycles in any list, is simple, and efficient with ON time and space. In the worst case, the time complexity of this algorithm is ON. Here, n is the number of nodes in the linked list. Even though we have 2 pointers moving at different speeds, each node is visited at most a constant number of times. Now, let's look at the idea behind this solution. We use a technique called Floyd's tortoise and hare. We have 2 pointers. The slow pointer moves 1 step at a time. The fast pointer moves 2 steps at a time. If there is a cycle, the fast pointer will eventually catch up with the slow pointer. If there is no cycle, the fast pointer reaches the end of the list. We start by setting up our function to detect a cycle. First, we check if the list is empty or has only 1 node. If it does, it's impossible to have a cycle, so we immediately return false. Next, We create 2 pointers. The slow pointer starts at the head of the list and moves 1 node at a time. The fast pointer also starts at the head but moves 2 nodes at a time. Think of it like a hare running faster than the tortoise. We now start a loop that continues as long as the fast pointer hasn't reached the end. If fast reaches the end, we know there is no cycle. Inside the loop, we move the slow pointer 1 step forward. We move the fast pointer 2 steps forward. Then we check if the slow and fast pointers meet. If they do, it means there is a loop in the list. We've detected a cycle. If a cycle is found, we return true immediately. If the loop finishes without the pointers meeting, the list has no cycle, so we return false. So, to summarize, this algorithm sets up 2 pointers at the start of the list and moves them at different speeds. If a cycle exists, the faster pointer catches up with the slower one. It is efficient, simple, and elegant. This method uses 2 pointers, slow and fast. The fast pointer eventually catches up if a cycle exists. It requires no extra memory, so space complexity is O1. The worst-case time complexity is ON. Now that we've implemented our solution to detect cycles in a linked list, let's see it in action. We test it with 1, 2, and pos equals 0, meaning node 2 points back to node 1, forming a cycle. The function uses 2 pointers. Slow moves 1 step at a time, and fast moves 2 steps. If a cycle exists, fast will eventually meet slow. Otherwise, fast reaches the end. For this input, slow and fast meet, confirming a cycle. The output is true, showing that the implementation correctly detects the cycle. This 2-pointer approach efficiently identifies cycles, works for any list, and is simple, accurate, and reliable. Breakdown recap. Conceptually, we're given a singly linked list, and we need to determine if it contains a cycle, that is, if any node points back to a previous node instead of ending with null. If a cycle exists, we return true. Otherwise, false. Assess recap. We looked at different approaches. A brute force method is to store visited nodes in a hash set, but that uses extra space. A more elegant solution is the tortoise and hare technique, 2 pointers moving at different speeds. If there's a cycle, the faster pointer eventually catches up to the slower one. If not, the fast pointer reaches the end of the list. This method gives ON time with O1 space, highly efficient. Structure recap. Our approach was straightforward. Initialize slow and fast pointers at the head. Move slow 1 step at a time, fast 2 steps. If they meet at any point, a cycle exists, return true. If fast reaches null, no cycle exists, return false. Implement recap. We implemented this using the classic 2-pointer method. Running it on LeetCode, the code executed cleanly, detecting cycles or confirming acyclic lists without errors. Check recap. We verified it with multiple cases. Lists with cycles, like one where node 5 points back to node 2, correctly returned true. Lists without cycles returned false. This confirmed that the logic works as expected in all scenarios. Closing insight. The key takeaway? Cycle detection is all about pointer strategy. By carefully moving slow and fast pointers, you can catch loops efficiently, using constant space, a small trick that demonstrates big mastery over linked lists.